Dirac. Today we will be working on impulse functions, also known as Dirac delta function. These functions are mostly used in physics to express an instant force, an instant vibration, and this is why when we're dealing with impulse functions, the graph of these functions are zero except for one point where the amount is 1. Obviously, physics people usually scale it, so at that moment you're not going to get a 1 but some other number, but the basic delta function, the impulse function, will have a 1 there, so that's how we express these kinds of behaviors in real life. So delta function, direct delta function, is expressed by delta parentheses t minus a, where a is the point on x-axis. Let's say it's a, like here, and all the way it's going to be 0, but at this point it's going to be a 1 and continuing to be 0. So let me further show it to you. The graph should look something like this, where point A has a value of 1, but the other points will be remaining 0. And this is why these functions really play an important role in life. So t minus 8, obviously a represents the point where it's 1. This is not a continuous function, important to note, which is why we're not able to take a derivative for this point. Other than that, this is pretty much what the direct delta function is. And a basic informal definition would be 0, t minus a direct delta would be 0 for all t except when t is equal to a, and when t is equal to a, direct delta function t of t minus a would be equal to 1. Just like step functions, unlike step functions, remember how step functions would switch. It would continue to be 0, and then at a point ta, where step functions defined as t minus a, we would have a 1, and that will be keep going. But similarly, we do have similar behavior, but it wouldn't keep going as 1, but it would just get back to 0. So it's just an instant switch compared to step functions, where step functions is just like a light. When you turn it on, it's on. When you turn it off, it's off. Okay? So the integral of direct delta function is going to be equal to 1, because if we're taking the entire xy plane, entire x-axis, there must be a value that direct delta function is going to produce 1, and the area of that little vertical line would be equal to 1, and the rest would be equal to 0, so the area under the curve would be equal to 1 for negative infinity to positive infinity. Now, if we go for a little example, since the integral of direct delta function from negative infinity to positive infinity is equal to 1, when we multiply with the function, we're going to get the value of the function at point A. So basically, when you multiply a function with direct delta function and take the integral, your result is going to be f of a, where a is the point 1, when the y-axis is equal to 1 for a direct delta function, your function is going to get the f of a value, where a is the x-axis coordinate of the direct delta's function, where it's equal to 1. So let's work on this example. So we know that direct delta function, when we multiply a function times a direct delta function, we're going to get the function of a. Well, the direct delta function is equal to 1 from negative infinity to positive infinity. So we're going to say f of a if I consider my function f of t equals to 5, because this is a function, right? You could say 5 times t to the 0 power, which is still equal to 5. A function of t could be expressed by this. We're going to say f of a, and f of a in this case is going to be 3, because direct delta function switches at 3. So f of 3. And what is f of 3 equal to? Well, f of t is a 5, which doesn't include a variable, so it's still going to remain a 5. So this integral, this indefinite integral, this improper integral, I should say, would be equal to 5. Okay, so let's work on a little bit more interesting examples. The Laplace table, as shown below, will be like this. Taking the Laplace of a direct delta function will give us e to the negative as. So similarly with step functions, we would have an e to the negative as, but we don't have a denominator of s for the Laplace of direct delta function. And important to note that a must be greater than or equal to 0 so that we could satisfy this Laplace. Well, since this Laplace is an integral, guys, if we're multiplying a constant with another a function, well, we can pull the constant out of the integral. Do not forget that Laplace is actually an integral. It's not a magic we're doing here. It's just an integral defined by a set of rules. So when we have a constant, we can just pull out that constant and take the integral of Laplace of direct delta function. I know they look kind of similar when you draw it, but hopefully you don't mix those letters up. And when you take that Laplace, well, that's going to be, 1. I'm sorry, that the Laplace will be e to the negative as. And, the constant outside, the constant could be carried outside, and we would have c. Okay, so if you put the c outside, you're going to obviously have it on the right-hand side as well. Now let's solve this very good Laplace problem. Well, initial value problems with direct delta functions in differential equations or calculus 4 should look pretty much like this. You're mostly expected to know the Laplace of direct delta functions. So just like we solved every Laplace problem, what we're going to do is take the Laplace of y prime, and what Laplace of y prime is going to be s y of capital Y of s minus y of 0 plus capital Y of s for the Laplace of y equals to, and we note that we said e to the negative as is going to be the Laplace for the direct delta function. So e to the negative as in this case will be e to the negative, and a is going to be 2. We call a the value of this part e to the negative 2s. Okay? And this is pretty much the basic setup. And just like we did for every Laplace equation, what we're trying to do is find what y of s, capital Y of s, equals to. We want to solve for y of s. And then using inverse Laplace theories, we're going to get the y of t function. And y of t is basically the solution of this first order differential equation. Well, y of 0 is given to us that it's equal to 0, so we're just going to ignore that. And I'm going to factor out a capital Y of s here. And we're going to have s plus 1. Okay, and we didn't do anything on the right-hand side of the equation. And this is how it looks like. And if we go ahead and take another step, we could see that this is equal to e to the negative 2s over s plus 1. And please pause this video and try to see what kind of inverse Laplace we are dealing with. So I hope you were able to understand what's going on here. This is the shifting theorem. And as you can remember from the previous lecture on step functions, when you want to take the inverse Laplace of a function e to the as multiplied by f of s, or in other words, if we were given this function and we wanted to take the Laplace of it, we would get this. So the domains actually do change. Okay, so if you're taking the Laplace of a function multiplied by a u function, a step function, the input of this function is going to increase by a, but when you're doing the opposite, you're going to decrease the input by a of the f function. So in this case, since we're doing the opposite, we're taking the inverse of this Laplace, our input of our function will decrease by a. And what a is dependent on the u function, the step function itself. So first of all, what we will have to do is notice the e term. Okay, the e term is what? E term is e to the negative 2s. So e to the negative 2s. Well, if we think about this as an inverse function, inverse of step function, this a would be equal to, it's going to be equal to 2. So we're going to have u of 2, or u of t minus 2. Okay, because if we took the Laplace of u of 2, we would get e to the minus 2s over s, but from the shifting theorem, you know that you get this e to the negative 2s due to this step function's input. So we have a u to the t minus 2, but now what we are left with is 1 over s plus 1 as our capital F of s, okay? Well, here's the thing. If you want inverse Laplace, you have to subtract a from the domain of the function. However, we still haven't gotten the function yet, so first of all, you want to take the inverse of this. And the inverse of 1 over s plus 1, you should already be memorizing that, is going to be e to the negative t equals to f of t. Well, notice we got f of t, but we didn't get f of t minus a, and a is equal to 2, so f of t minus a will be you're gonna substitute t minus a everywhere you see a t, so we're gonna have e to the negative t, actually negative parentheses, and our t minus a is gonna be t minus 2 because of the step function, so we're gonna have t minus 2 here. So f of t minus a is gonna be equal to e to the 2 minus t. So you're gonna multiply that with the step function e to the 2 minus t. Okay, and this is actually equal to our function y of t. So we were able to take the inverse of this function, this Dirac delta, this impulse function, and this gave us a step function representation. So notice how they are actually working together most of the times, and this is what's going to happen most of the time when you're solving differential equations involving Dirac delta function. You're going to most likely see a step function because it comes from the step function. So basically, in summary, what we did was we built this equation to represent the Laplace of the left-hand side and the right-hand side. Using the given initial condition, we were able to simplify it a little bit, and I factored a y of s, and then we solved for y of s, and we wanted to take the inverse Laplace, but I reminded you guys that that shifting theorem is actually we're going to work with step functions, and we're going to have a step function in the result and a t minus a as the input of the f function. And we were able to find the respective inverse Laplaces, and which this generated our final result of u of t minus 2 e to the 2 minus t as our solution for this differential equation.